Are you recording? Oh, now it is. Okay. Alrighty, so had a question on the red blackness. Nope, that's not what I want. There we go. Alrighty, so if we look, let's just draw up a basic and then we have our second loop. Okay, so this is our normal Jacobi or Gauss-Seidel loop that runs in serial. Yes? Okay. So, that's not what I thought that was. Now the question is, how do we get that to run, do our red-black scheme? So, if we have our grid here, this is running through these basically like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just in this order. Okay? Now, the red-black scheme, what we're doing is we're taking this domain and we're splitting it up. And so we're going to mark every other node as red. Okay, so we're going to take our one loop and split it into two loops. The first loop does all the red nodes. The second loop does all the black nodes. All right, and so, for instance, the red loop here would look something like this. And this may or may not be completely correct, but it should get you the idea. Oh gosh, I'm running out of room here. Can I? Nope. I plus equal 2. And you do the same thing on J. J plus equals 2. And then the black loop is going to look something like this. This time we're starting at 1 and running through N. And we do the same thing with J.
Shouldn't I still start in the same?
No.
No, because if it starts at 0 here on both loops and you increment by 2 every time, you're only going to do the red nodes. So you have to start at 1 and increment by 2.
Because it's shared memory.
Because we're doing shared memory.
So it's all the same.
Right, but isn't I like the column? So we're not going to use the first column at all for I.
What?
Well, I said that this may not be technically correct.
Right.
You've got to figure out the nitty-gritty details. But this is the basic idea. You skip by 2, and so we have 2 loops here. And we can parallelize each loop. Like that.
So, okay, so that makes sense to me for 2 processors. Does that work for more than 2 processors?
It does. Basically, since the red nodes are only dependent on the black nodes, okay, we can have 12 processors compute red nodes. And so this one processor gets that node, one processor gets that node, one processor gets that node, because they're not dependent on each other, and so they can all be run at the same time. Does that make sense?
Yes. Okay, now how about the CC Numa stuff, though? How does that work?
So for the CC Numa stuff, all we're doing is initializing, and we have to initialize it in the same way we run through the loops. And so I would do, I mean, this may not be the best way, but what I would do is set up a red loop that runs through the red nodes and parallelize that in exactly the same way and say Pij equals 0, and then we do a black loop that does the exact same thing. So the initialization loops should have the same structure as the actual computation loops. Does that make sense?
Yeah. I'll just have to try it and see if I get it.
Okay, sounds good. Alrighty, now how do I get out of this thing? Exit. Okay. So the Parallel Jacobi project is due tonight. And then there's a quiz due on Saturday. And I will try and post your first MPI project today. So that's what we're gonna talk about is MPI. So MPI is basically a really big game of telephone. You ever played that as a kid or college student? Sometimes college students do things like that too. We love to go back and play Pokemon on our Game Boy, right? Alrighty. So, when we're talking about message passing, there are a couple things you need to know about the network. I said last time we wouldn't be talking about the network. I lied. But there are some important things to know. First off, that every network has a latency associated with it. Latency is the amount of time it takes to transmit a message of size 0 bytes. This is very similar to when you ping a website. Anybody ever seen that? Or if you go to speedtest.net. Okay.
By the way, here it's ridiculous how fast the internet
Yeah. Okay, so this is basically measuring this ping. This is the latency of the internet connection is 2 milliseconds. Okay, so that's really good. And here they're testing the bandwidth as well. So this is your bandwidth. This is your latency. Megabits, not megabytes. So it's divide that by 8 to get megabytes.
Well, my phone was probably like 2.
Yeah, mine as well. Okay. So there's your simple test. 2 milliseconds is really good. That's on the order of it's on the order of what they have in the InfiniBand. CHPC, I read one of their help pages and they said that their InfiniBand latency is like 1.75 milliseconds. Okay, that's just how long it takes to basically say hello and send back a hello. Okay, you're not actually transmitting any real data. Every network then has a maximum bandwidth, which is the maximum amount of data that can be transmitted at any given moment. And then effective bandwidth is how much of a network your program is using. This can be measured with a ping pong program. There's a listing in the book. Basically, all it does is say hello, and it transmits a given amount of data. 04.51. So for those of you at home, here is their example on an Ethernet network. Okay. Hopefully you can see that. And for those of us here, it looks something like this. So on the bottom axis, they have the number of bytes that were being sent. And then this is the effective bandwidth. And this is log scaling. So just so you know, we have like 10 to the 1 and then 10 to the 6. Okay, so down here, this is what we call the latency dominated region. You can see that our bandwidth is not very good until we get up here in this region. This is the bandwidth limited region. And so latency is always present. And then we have equations 4.1 and 4.2. So if we take the time, the total time it takes to transmit a message is going to be the latency time plus then the amount of data being sent divided by the bandwidth. Okay, the bandwidth is 10 megabytes per second. Then if we have 10 megabytes, that's going to be 1 second. Does that make sense? And then the effective bandwidth is the amount of data being sent divided by the time it took to send it. All right, so this basically says it took X amount of time to send this. So this is in terms of seconds, and then this is in terms of bytes. So our effective bandwidth then is bytes per second. Okay, and so you can measure the effective bandwidth with the ping pong program, where they basically just send data back and forth to each other. And so in general, this is important because you generally don't want to send lots and lots of small messages, because then you're not using bandwidth to its full capacity. You're limited by the latency. And that latency adds up for all the small messages. Does that make sense? Okay. All right, so when we're sending or receiving a message, there are some important things you need to consider, and these questions come from the book. Which process is sending the message? Where is the data on the sending process? What kind of data? How much data? Who is receiving it? Where do we need to put it when we get it? And what amount of data should the receiving process be prepared to accept? There's a lot of details that go into this, and this is why people like OpenMP, because they don't have to worry about all this stuff. But all MPI calls specify these questions in some way. Okay. All right, so now we talk about how does your data actually get sent from processor 1 to processor 0, or processor 0 to 1. So you have your data, you've allocated your arrays, and you need to send it. So you use the MPI library, and well, the MPI library could have a buffer, and so it actually copies your data into the buffer. From there, it sends it through the network. On the receiving end, it comes out of the network, gets copied into the MPI buffer, and from there gets copied into the arrays that you have on processor 1. Right? So that's one way it could happen, but there's a lot of copying that goes on in there, and copying takes time. So you could do it this way, where you take your data directly and send it through the network and receive it directly into your arrays. And there's advantages and disadvantages to both of these. So there's when we're dealing with MPI, we're going to talk about two kinds of messages, a blocking and a non-blocking message. So a blocking send waits until the user-supplied buffer is free to be changed. So if we have a call here, MPI send, okay, and we give it some data, all right, it will not return from this function until you are safe to modify your data. Does that make sense?
Yes.
Okay. So that's one thing that's nice about the send is the send function is you know for sure that you can go ahead and change that. So a non-blocking send does not wait. A blocking receive waits until the user-supplied buffer has been filled. So on the receiving end, we have a call that looks like this. MPI receive. And you're going to give it, you're going to say, okay, I want you to put the data that you receive in this particular location. Okay? And that will not return until that buffer has been filled. Does that make sense? Okay. So at that point, after this call, you know you are free to actually, run through your loops and whatnot. Because MPI is done with it, basically. However, a non-blocking receive does not wait. And in all situations, you have to be careful that you avoid what's known as a deadlock scenario, where processors are waiting for messages that just aren't coming. And so one processor is sitting there, I need a message, and everyone else is like, where the heck are you? Okay. So now we're going to talk about the MPI send and MPI receive functions. These are the most basic functions available for sending and receiving data. And these are their declarations. This is what they look like. They take a pointer to your data. They take then the amount of data, the type of data, where that data is going, a tag for what type of message this is, and then the communicator. And I'm going to talk about each one of these over the next few slides. On the receiving side, you'll see it looks pretty much exactly the same. The only difference is now we have a source instead of a destination where it's coming from. And then we have this funny thing called an MPI status. So buff, again, is a pointer of what needs to be sent or where you want to put received data. Count on the sent side is the number of data items to be sent or the maximum number of items to be received. You can actually receive less than this number. It's not an exact number, unless, of course, you write your program that way.
How does it know?
What do you mean?
Well,
How does
I mean,
it know
if you can,
what?
If you can receive less than that, then how does it know when to stop receiving?
I'm going to talk about that.
Oh, okay.
Yeah. Type of data, where it's coming from, where it's going to, the tag, and the status. Okay. So the data type. The data type is going to be one of these here. Okay. These are the MPI specified types. And then these are the actual C/C++ types that they map to. So if you want to send a double, you want to use the MPI double here in your data type. Note, it is also possible to define your own derived data types. That's more of an advanced topic that we won't be getting into. unless someone has a hankering to really know that. But so that's pretty simple. This is a shorter list. There's actually like twice as many as of these. But anyway. All right, so the destination, source, and tag. These are really important because what we're doing is we're specifying what's known as point-to-point messages, where we're sending from one person to another person. In order for a message to be received, all three of these have to match. The destination and the source and the tag must all match. Generally, your tag can be just 0. Okay, that's what I always do. I haven't really had a situation where I've needed tag. You can set the source to be an MPI any source, which basically matches any message, and an MPI any tag is also an option for your tag number. And this matches, again, any tag. Another important thing to note, MPI does not preserve the temporal order of messages unless all three of these match.
What does that mean, the temporal order?
So let's say you have processor 0, 1, and 2. Okay, processor 0 sends a message to 2. Processor 1 sends a message, and then processor 0 sends another message. It is possible, these were sent in this order, 1, 2, and 3. It is possible for message 2 to arrive before message 1, but it is not possible for 3 to arrive before 1. Because 3 came from the same processor. All right, the MPI communicator. This describes kind of the whole kit and caboodle of your whole thing. Describes the processors that are running and how they relate to each other. The MPI library always has a default communicator called MPI COM World. So if you ran the following statement here, MPI COM World then describes the entire world of all 4 processors. And then it is possible to create your own communicators, which are either subsets of this or rearrangements of MPI COM World. And we're actually going to get into that in a Cartesian setting. Anyway, then every processor in a communicator is assigned a rank. A processor can be part of multiple communicators and have a different rank in each communicator. So if this is our world, and they are assigned the following ranks, 0, 1 through 2, and 3, and then you define a new communicator that just contains these 2, it is possible that in this subset communicator that we have ranks of 0 and 1.
What's the benefit of assigning them to different communicators?
Depends on where you need to send information.
So you could define, I mean, it really depends on your problem that you're solving, but it is possible to have, say you have like 3 or 4 different tasks that need to be done. So you take your MPI COM World and you split it up in 3 different subsets.
Basically, you're splitting up into different project groups.
Exactly, different project groups. Okay. And then the very last thing is this MPI status. And this is a very simple struct containing information about a received message. And here's a little code example here. We have declare a variable of MPI status. We have our receive call. And if we were using, say, the MPI any source, this is where this becomes really helpful, is the struct member MPI source contains where the message came from. MPI tag gives the tag of the message. And then you can use count. So we have just declare a variable count, and then we use this function, MPI get count. We send it a pointer to our status struct. We tell it what type we want out of it, and then it tells us how many of those were received. So that is how you determine how much data you actually got. So the MPI receive count number is just a maximum number. And that's to prevent MPI from running past your buffer and having memory problems. And so this is how you actually determine the exact number of items that were given to you. Does that make sense? Okay. So now I'm going to do what I've titled the MPI parable, or as I like to call it, the parable of Larry. So, here's you. Here's Larry, your cousin Larry. And both of you have whiteboards. And you have some data on your whiteboard that you want to get to Larry. Unfortunately, there's a big ocean in between you and Larry. So, both of you have access to an MPI guy. Okay? The MPI guy has his own whiteboard. So you go to the MPI guy. This is number 1 here. You go and you say, hey, look, I have some data I want you to send to the other MPI guy. And he says, great. So he writes down your data. He copies your data onto his whiteboard. Then he calls the other MPI guy and says, hey, the data is number 4. So he writes it down on his whiteboard, number 4. And then Larry comes to the MPI guy and says, hey, what's the data? And he says, it's number 4. At which point he writes number 4 on his whiteboard. So your data has now been moved from you to Larry. So this is what they call a blocking buffered send.
What's that number 2 arrow mean?
I missed that part. So he copies his data onto his whiteboard. He copies the data onto his whiteboard, at which point he says, okay, you're free to go. I have the data, I will get it sent. And so number 2 is you leave. Okay? And so this is how MPI handles this particular situation here. Okay? Now, here's a different scenario. Let's say you have a really big whiteboard, bigger than MPI guy's whiteboard. At which point he says, that is too big. I am not going to let you leave until I phone this information over here. At which point Larry, who also happens to have a really big whiteboard, writes down the information as he gets it from MPI guy. Okay, this is what we call a blocking non-buffered send. It's also known as a synchronous send. Because in this situation, you could leave, and you didn't care when Larry got the information. You were just secure in knowing that the information was being sent. But here, both of you have to be there at the exact same time in order for the data to get sent.
So both of those are done through MPI send?
Here's why I tell you this. The MPI standard does not say how MPI send should work. Okay, so generally what the implementations do is when you have a small message, they do this first situation. But when your message gets too big, you get the second situation, which can lead to deadlocks. Okay, so if you write a program assuming this is going to happen, but this happens, you can end up in a situation where Larry is not there. And so you spend forever sitting there waiting for Larry to show up. And that's this situation here. So you are trying to send information to Larry, and the MPI guy won't let you leave, okay? Because he can't copy your big whiteboard onto his little whiteboard. So he's sitting there, he's calling the other MPI guy, who is sleeping because he's lazy. And his phone is buzzing there. And Larry has not come to say, hey, wake up. Right? This is what we call a deadlock. Is you are waiting, you are blocking until the message gets sent. Does that make sense? Because
But it's not getting received.
but it's not getting received. Exactly. All right, so there are ways, and we'll get into this, of how to do a non-blocking send. So you, instead of copying data down over to a whiteboard, you just give Mr. MPI guy a pointer to your whiteboard so he can see what it looks like. Okay? And so then he's like, great, I have a pointer. I can see what your whiteboard looks like. You're free to go. At which point, you then can wander off and do whatever you want. But you decide, hey, I need to change my 4 to a 0. Okay? So that's step 3. Step 3.5, you change that number to a 0 when MPI guy is in the middle of telling the other MPI guy what it is. And so he ends up with this mix of 4 and 0, which he then gives to Larry. And so basically Larry gets garbage because the buffer was not available yet, but you didn't know that. Does that make sense? So done correctly is this. You give him a pointer, and you then go do something else. Okay, you go watch Netflix. At which point, once you're done watching Netflix, you come back and you say, hey, Mr. MPI guy, are you done yet? And if he says yes, then you can go on your merry way. If he says no, well, then you go back and watch more Netflix. Or you wait. Okay? Confused look.
From the blocking send.
You specify.
So in this case, instead of watching Netflix, you could do something useful. So this is what they call overlapping computation with communication. And so a lot of people, basically the idea is you start the communication in the hopes that MPI can do that while you are doing computation at the same time.
Somewhere else, though.
Right. So you can do computation on something else that doesn't involve this particular whiteboard, this particular memory.
In a blocking send, you just have to wait.
You just wait.
Right. Well, I understand that, like that you can go do something else. I was just curious because this guy, if you don't have the receive command over there, he's still going to be waiting forever to use that bit of memory that you're sending.
So MPI will be waiting forever, but you won't. So generally in an implementation, sometimes in a network, each processor will actually have a dedicated piece of hardware to handle network communication. And if the MPI library knows that, then it can start a thread, a separate thread, on that dedicated hardware that doesn't interfere with the CPU.
Right.
And so you can do two things at once. You can communicate and compute at the same time.
I guess I'm just curious about the number 4 arrow down there
Okay.
compared to in the previous one, because like this one is still waiting for the MPI to finish communicating, right?
No.
To the
This
degree.
one?
So this one is for sure, right?
No. So this is
Oh, sorry, no, not this one. The one before.
one before.
This one, right?
Okay.
This one is waiting for MPI guy to finish. Won't do anything until it's done.
Right.
Now go 2 slides ahead. This guy, however, he's not waiting necessarily, but he is still going to go to the MPI guy and say, "Hey, are you done yet?"
He doesn't have to.
But if we're doing it correctly, we want to, right?
Right. Right. So you'll see here the problem is on the receiving end.
Right.
Okay. Here I've assumed the receiving end is set up correctly.
Okay. So if the receiving end isn't set up correctly, this will still not change
Right. This will
Yeah.
still end up in a deadlock.
ever.
Yes. Exactly. Because you'll be sitting here doing this.
Doing just something useful until you get the done message.
Right.
Technically, you don't have to wait for it, right? I mean, you can keep going on, so it's not
At some point you will want that data though.
right.
At which
But-
point you have to receive the confirmation from MPI that it has been finished.
Which, if you have that coded in and you're still waiting, then you're not going to move on past it.
Right.
Right. This
So there's 2 functions that you can use here.
this is just more customizable, basically.
Right. But either way, it can still end up in the block. Is
Right.
what I was asking.
Right. In a blocking send, MPI basically does it all for you. In non-blocking send, you have
You
to
can tell it
specify.
You can tell it to wait.
Yeah.
So there's 2 functions. MPI test, what that does is it tells you yes or no. I am done or I'm not done. Okay. MPI wait actually stops and waits for it to finish. Okay. And so, depending on your situation, you could use either one of these. But usually in the end, you will end up with this wait command. I am waiting for something to happen. I'm waiting for this message to finish sending so I can actually go on and use that buffer in the end. But we do this in the hopes that by the time you're done watching Netflix, it's already done. And so the waiting command doesn't actually do any waiting.
Just tests and moves on.
Yeah, exactly.
This is easier to troubleshoot too, I'm guessing. Compared to blocking. Because the blocking, you don't know what's going wrong necessarily. But this one, if you end up waiting,
Yeah.
you know that you're not.
Yeah.
Well, blocking, you should for sure know what's going on because you didn't set up your receiver right. Right? I mean,
Basically. Another thing to note, there actually are a couple. There's. All right, so then there's actually MPI B send, which everyone says don't use, because in general, using the asynchronous command is easier. And then there is the MPI S send, which is not buffered, but it forces synchronization. And then this is the I send, which stands for immediate. It doesn't wait, it returns immediately. And then the blocking synchronous send, which is S send, like I mentioned previous. This is how it works. So you give your data to the MPI guy. I didn't write labels on these guys. No. Okay, he calls over to the other side. The other MPI guy says hello. At which point, MPI guy says, okay, we're good to go. I'm going to send the message now. You can leave, and he finishes transmitting the data, and then there's the next copy. So the synchronous send doesn't actually wait until the entire thing is over. It just waits until there has been a connection. And that is the parable of Larry. And once you understand these concepts and how these scenarios are set up, it makes using MPI so much easier. Because if you don't understand it, you're going to screw yourself over because you're basically going to end up in a deadlock situation. And we'll get more into detail. I guess we got a few more minutes. Go ahead and keep those. We can get into a little bit more detail here. All right, so any questions on any of that? Let's do this, actually. We'll just do this. I'll just write some pseudocode up here. So let's say we have our MPI program. And so we have our init, and we figure out we have 0, let's say we have 10 processors. Okay? We have 10 processors. And so this is our game of telephone. Process 0 is going to generate a random number. And you want to pass this random number down the chain to the end, at which point processor 9 is going to spit it out to the screen. Okay? So let's say we do this. Let's have int from equals rank -1, int 2 equals, actually let's just send this. It's actually going to send it back to processor 0. So we have a circular shift here. Okay, so does this situation make sense?
Yes.
Okay. So then we're going to do just a simple all right, so what's wrong with this scenario?
There's no weight.
Well, I'm using the blocking commands here.
Oh, wait, what are you sending and what are you receiving?
I'm sending a random number from
Rank
0.
Made a number, but rank 1 won't have anything to send until it receives.
Exactly. So
You assume that you
let's
put-
change the situation. Let's change the situation. Sorry. Let's say everybody generates a random number. And they're all going to move it over to the left or right. Okay? Everybody has a random number, and they're all going to send it to the next guy on the right. So now what's wrong with this? That should make a little more sense.
Where's it going? Because it's going to get copied to that we don't know what order it's going to happen in. So we could be sending the random number generated at 0 all the way to 9. We don't know because. Does that make sense? Where's it?
Everyone's
Where's it being
everyone's
copied?
trying to send, but no one's able to. They have to send before they can receive, but nobody can receive it.
That's the problem. They're all trying to send, but there's no receives. No one has gotten to the receive function because they're all
Waiting at the send.
they're all waiting at the send. That's the problem with this. Now, it could happen that if the MPI implementation decides to do a buffered copy, so it buffers the random number, and then it says, okay, your data is free now, and so your program moves on to the receive, at which point everybody receives the number. Does that make sense? So in that case, it works. But let's say now you have 100,000 random numbers you want to send. Now it's not going to do a buffer, and so now it deadlocks. And that's why this MPI send can be a little tricky if you don't account for the possibility that it could deadlock. However, the MPI people recognize this, and so they actually have another function. So we can get rid of this altogether. Called MPI send receive, which is guaranteed not to deadlock. That they don't care how you implement it as long as it never deadlocks. It's a combo routine that does both. And this is what's called a ring shift pattern, because if you form these into a circle, you are shifting around the ring like this. And there's another way around it. You could put an if statement in here. If oops, how do I erase that? Is equal to 0, send receive, else okay, so what is this doing?
Those half the processors just send first. And the other
Which half?
first. The ones that
Even
are,
ones.
The even ones. Yeah, exactly. So the even processors are sending first while the odd processors are receiving. Okay, so now we have matching sends and receives, and there's no deadlock. And then we send and receive. And so that is a way to break the ring shift deadlock, as it's known. And so these are things that you need to think about when you're actually writing MPI programs. So anyway, that's going to be our time. So anyway, any questions? Nope. Okie dokie. Well, we'll see everybody tomorrow then. Turn this